In this video, we're going to be proving two special trigonometric limits. The first one we're going to be looking at is limit as x approaches 0 of sine of x over x. Let's look at the unit circle. Let's pick some point here. And let's draw down a perpendicular to get a right triangle. And we'll call this angle theta. We'll call this angle theta. Let's draw over it again. Okay. We know this is some point x comma y, but because it's a unit circle, we knew that cosine is x and sine is y. So this point right here, we can represent it as cosine comma sine. And we know that this point right here is 1 comma 0. And I'm going to draw this line down here to be a part of that triangle. I'm then going to extend the triangle all the way up, and then I'm going to join with this line. Okay, and then this is going to be 1 comma tangent theta. Okay, because we have this right triangle, the angle is theta, the adjacent side is 1. So tangent theta is the opposite over adjacent. So this side is 1. Okay. So let's look at these three special triangles closer. So the first one we're going to be looking at is the big triangle. So we're going to have this triangle. The angle is theta. The base is 1. And we said the height is tangent theta. Then we're going to be looking at the part of the sector that is basically part of the triangle and the unit circle. So it's going to look something like this. So that's going to be, I'm going to highlight it, it's going to be basically this part right here. Okay, so we have radius 1, angle theta. And then we're going to be looking at this triangle right here. This whole triangle. So let's draw that out, see how it looks. We have this triangle and this perpendicular drawn down here. We know the entire base is 1 and the angle here is theta. And we know the height is sine theta since that's the y value. Okay, let's look at all the areas. So the area of the first triangle, that's 1/2 base times height. The height is tangent. So we can just say the area is tangent over 2. The next is the area of a sector. We know the area of a sector is 1/2 r squared times theta. The radius here is 1 and the angle is theta. So we say theta over 2. The last one is a triangle with base 1, height theta, or height sine theta. So it'll be sine theta over 2 is the area. Now let's consider an inequality. We know the triangle all the way at the right is part of this sector. Right, this part right here, if I combine this red region, is basically this right here. So this small triangle is smaller than the area of the sector. So this has to be less than or equal to the area of the sector. And we know that the first triangle is the sector, but it's extended. Let's try that again. So it's basically the sector, but it's extended up here. So that has to be bigger than or equal to the sector. So this argument has to just deal with areas. Okay, so let's see. I have tangent of theta over 2 that is greater than or equal to theta over 2 greater than or equal to sine theta over 2. Okay, so now I'm going to be multiplying all the sides by 2 over sine theta. So let's see, tangent is sine over cosine. So this will be sine over cosine all over 2. And I'm going to multiply that by 2 over, let's see, 2 over sine theta. And that's going to be greater than or equal to 2 over sine theta times theta over 2 greater than or equal to sine theta over 2 times 2 over sine theta. Now a lot of the things cancel. The 2 cancels with the 2. The sine theta cancels with the sine theta. 2 cancels with 2. Sine theta with sine theta. 2 and 2. So now I'm left with 1 over cosine theta is greater than or equal to theta over sine theta greater than or equal to 1. Okay, so my limit, my special function was sine theta over theta. So I want to flip everything. So I'm going to flip 1 over cosine to be cosine. I'm going to flip theta over sine to be sine over theta. And then 1 is just 1. And because I'm going to flip, I'm going to switch the inequalities. And now I'm going to take limit as theta goes to 0 for all of these. So I'm going to take a limit as theta approaches 0 for cosine theta, and limit as theta approaches 0 of 1. In both cases, the limit is equal to 1. So not only does cosine go to 1, sine also goes to 1. So by the squeeze theorem, sine theta over theta has to approach 1 as theta approaches 0. So we say that limit as theta approaches 0 of sine theta over theta is equal to 1. And that concludes our proof. Okay, let's try another proof that involves cosine. Let's see what that looks like. We're given limit as x approaches 0 of 1 minus cosine over x. We want to prove that is equal to 0. So the first thing we're going to do, let's rewrite everything. And we're going to multiply by the conjugate of 1 minus cosine. So we'll multiply both sides by 1 plus cosine. So I have limit as x approaches 0. Here on the top I have a difference of 2 squares, so it's going to be 1 minus cosine squared. And that's all going to be over x times 1 plus cosine x. we know 1 minus cosine squared is sine squared. So I'm going to replace that, and I have x over 1 plus cosine x. I'm going to rewrite this. So I'm going to have limit as x approaches 0, and I'm going to break up the sine squared. So I'm going to break up the sine squared as sine over x times sine over 1 plus cosine x. So here I broke up the numerator and the denominator. Okay, I know from the last proof that limit as x approaches 0 for sine x over x, that's equal to 1. Right, so this thing right here is equal to 1. So I have 1 times sine x over 1 plus cosine x. So actually this I can get rid of the 1, so I can have sine x over 1 plus cosine x, and then I can just plug it in. I can plug in x equals 0. So I get sine of 0 over 1 plus cosine 0. Sine of 0 is 0. Cosine 0 is 1. 0 over 2, well, that's just 0. So we can conclude that limit as x approaches 0 of 1 minus cosine x over x is equal to 0.